Hello, everyone. I will report our work, weekly supervised video emotion detection and prediction via cross-modal temporal erasing network. The demo and homepage is listed below. To detect and predict video emotion, we research on video emotion recognition. It poses challenges for video emotion recognition due to the inherent characteristics of human emotions of ambiguity. Based on the observation of UGV, we find that the emotion evoked in UGV usually depends on multiple perspectives, and different frames in UGV may have unequal contributions to the conveyance of emotion. However, existing video emotion analysis methods assume that keyframes hold the dominant information for the intended emotions in videos, which is limited by that the selected keyframes cannot represent the intended emotions exactly. We now know that different frames may contribute differently to the conveyance of emotion, and the keyframe methods may not accurately represent the intended emotion. Based on this motivation, we improved the processing of keyframes' local information and proposed WECL. Our contribution mainly consists of 2 points. First, we build a weekly supervised network to exploit keyframes for erasing and extract features from multiple discriminative segments of video. Second, the intra- and intermodal relationships is investigated to erase local segments for learning robust and holistic representation from video. This is the outline of this report. Let's start with our daily life. When you are relaxing, have you ever used YouTube or other platforms to watch videos? Or have you uploaded your own videos on these platforms? They all belong to the platform of user-generated video, where users can create UGV and express their emotions and opinions freely. At present, there are a large number of UGVs, rich fields involved, and a wide range of creative platforms. When expressing the video uploader's point of view in UGV, the audience can feel the corresponding video emotion from the visual and auditory elements of the video. Video emotion is similar to image emotion, but video emotion has temporal changes and fluctuations. There are many application directions for sentiment analysis of UGV. On the one hand, it can help the platform to filter online content, removing disturbing and illegal content. On the other hand, sentiment analysis can also play a role in areas such as gesture recognition and customer behavior analysis. Emotion owns the nature of abstract, ambiguity, and perception subjectivity to be solved for obtaining effective model. For the ambiguity of emotion, emotion may compounded and overlapped with other emotion. For the abstract of emotion, effective cues for robust recognition may come from part of multimodal data, which is difficult to be extracted. For the perception subjectivity of emotion, there exists person bias due to various emotional-related attribution from viewers in videos. To detect and predict video emotion, we research on video emotion recognition. It poses challenges for video emotion recognition due to the inherent characteristics of human emotions of ambiguity. Based on the observation of UGV, we find that the emotion evoked in UGV usually depends on multiple perspectives, and different frames in UGV may have unequal contributions to the conveyance of emotion. However, existing video emotion analysis methods assume that keyframes hold the dominant information for the intended emotions in videos, which is limited by that the selected keyframes cannot represent the intended emotions exactly. We now know that different frames may contribute differently to the conveyance of emotion, and the keyframe methods may not accurately represent the intended emotion. Based on this motivation, we improved the processing of keyframes' local information and proposed WECL. Our contribution mainly consists of 2 points. First, we build a weekly supervised network to exploit keyframes for erasing and extract features from multiple discriminative segments of video. Second, the intra- and intermodal relationships is investigated to erase local segments for learning robust and holistic representation from video. The pipeline of our proposed model WECL will be briefly described below. Given a video, it naturally contains 2 types of modal, i.e., visual and audio. First, we use the feature extraction module to extract the features of the visual stream of the video and the features of the audio stream. Second, the temporal correlation learning module is introduced to model the intra- and intermodal relationship of 2 modalities. Then, the temporal erasing module erases the most dominant visual and audio information to generate difficult training samples online. Finally, the training samples are input into the model to find out more complementary information. In the feature extraction stage, similar methods are used for visual feature extraction and audio feature extraction. First, the video is divided into T segments, and information is extracted for each segment. The visual features are extracted by 3D ResNet 101, and the audio features are extracted by MFCC and 2D ResNet 50. In the temporal correlation learning module, 2 modality processes are included. For intramodal information, we exploit the pairwise correlation of video to model the long-range dependencies between different frames in each modal. The intramodal temporal fusion can enhance the extracted feature by capturing their global temporal dependence. Each modal has complementary information to other modalities, which is also beneficial to learn the relationship between different frames. So for intermodal information, we introduce a tension mechanism as the temporal correlation matrix extracted between video and audio features. Except for keyframes that directly evoke emotions, some other frames that contain background or context also play a very important role in understanding the emotion conveyed. In order to enable the model to also pay attention to the emotional information of other contexts, we introduce the temporal erasing module. In this module, we first build temporal attention, which enables the module automatically to find out important segments. Then, using the temporal attention maps, we can find the keyframes and erase them in order to drive our model to seek more complementary information. Finally, to learn representative features, our temporal erasure loss contains 3 parts from the original video, keyframes, and the left frames according to temporal erasing. We conduct experiments on the task of video emotion recognition and video emotion detection for verification. In the upper table, we show the accuracy of video emotion recognition on the test set of VIDEOEMOTION8, Ekman 6 and CAER datasets, comparing with state-of-the-art methods. As can be seen, audio can be regarded as auxiliary information to assist models to decide the better result. We could observe that methods using multimodal features achieve better results. Besides, our method obtains 2.8%, 2.9%, and 1.8% improvement on the video emotion -8, Ekman 6, and CAER datasets, respectively. The lower table shows comparison between our proposed method and existing SOTA methods on video emotion detection. Compared with other weakly supervised methods, ours improves mean average precision, which illustrates the effectiveness of taking intra and intermodal information into consideration and further finding out more complementary information via temporal erasing module for locating emotional segments. The table on the left presents the ablation experiments of modalities and modules, which proves that the combination of visual and auditory modalities has a certain effect on the performance improvement of the model, and also shows the contribution of different modules to the improvement of model performance. Finally, we show visualizations of our model. The left figure is the recognition result of emotional keyframe of audio stream, visual stream, and video stream. With the combination of vision and audio, multimodal information can help to accurately locate the position of keyframes. The right image is a visualization of detected keyframes. It can be seen that our method and labels are closer and more accurate. This is all my presentation. Thanks for your listening.